let's take a look at the CFU for 3.5. So one of the things you're going to notice is that the problems kind of repeat here. So we've already taken a look at this problem. Now we're just being asked to interpret different pieces of it. So just to kind of put us back in perspective here. So for number one, it's the problem that says some people think that the behavior of the stock market in January predicts the behavior for the rest of the year. So the explanatory variable is the percentage change in the stock market in January. So this is kind of it. I always find this very helpful and important to know. And that is the explanatory variable is the index, stock market index in January. Response variable to be the change in the index for the entire year. So it says we expect a positive correlation between X and Y because the change during January contributes to the full year change. So here is the data, the summary data collected. Okay? So A asks what percent of the observed observation in yearly changes in the index is explained by the straight line relationship with the change during January. So when you see this what percent, okay, you should be thinking about R squared. So notice how they give us R. Well, R is 0.596. So simply all I have to do is square both sides. Okay, so I'm basically, as you can see, squaring both sides here. So on my calculator, 0.596 raised to the second power. There we go, 0.3552. So I tend to go out 4 decimal places. So what we can say is 35.52%, and then I just pull it right from the problem, of the observed variation in yearly changes in the index is explained by the least squared regression equation. All right, that's all for A. B says for these data, S equals 8.3. So now it asks you to explain what that value means in the context of the problem. So remember that S is the prediction error. So what we can say is our least squared regression equation will have, whoops, I wrote with, that's funny, will have a prediction error of, and now 8.3, what is the Y value? The Y value is a percent. So we'll say 8.3% when predicting the Y value. So I got to put the Y value in response. So we would say when predicting the change in the index for the entire year, when knowing the X value, and the X value was when knowing the change in the index in January. All right, so that is our prediction error. All right, that actually takes care of number one, pretty quick and simple. All right, number two, we've already done this one in 3.4 where you're trying to find the line of best fit. So now here, just to kind of put us in the context here, it says below are the lean body mass and resting metabolic rates for 12 women who were subject to the study of dieting. Lean body mass given in kilograms is a person's weight leaving out all fat. Metabolic rate, calories burned per 24 hours at the rate body consumes. Basically, their lean body mass versus their metabolic rate is what we're trying to see. Is there a nice linear prediction here? So an A says, use your calculator to make a residual plot. Describe what this graph tells you about how well our line fits the data. So what I've already done in my calculator is I've put this data in list 1 and list 2. So we want to make our residual plot. Okay? So I'm going to try to make a residual plot here on my calculator and then graph it here also. All right, so now to get our residual plot, I got to go to, first I have to go stat, edit, and just show you that all my data is already in list 1. Remember, a residual plot is the observed value versus the predicted value. So to get those values rather quickly, first thing we have to do is go stat, calculate, and we actually have to perform the linear regression equation. When we do this equation, it will give us our line of best fit like we did in 3.4, but what it will do is it will generate a list of residuals for us. So to get those residuals, what we need to do is go ahead and highlight list 3 here. And now I want to put all the residual values in list 3. So they are already stored in the list menu. Okay, so if you go second stat, what you'll see down here is number 7, residuals. So you let list 3 equal the residuals, and it plugs those values in for you, which is really, really, really nice. Okay, so now if I want to do my residual plot, I can do it one of a couple ways. On my calculator, I go second stat plot, turn it on, select the scatter plot, and do list 1 versus list 3. Of course, once I have that there, I can hit graph. Of course, it looks like I got an old equation in there, so I want to delete that out. So I hit graph, doesn't show up. Zoom 9 helps it show up nicely. So now I can see my nice residual plot. So now if I want to graph that nicely, so if you're asked to graph one pretty nicely with a key of the scale, one of the things you should do though is go back to stat edit, and I'll show you how I graph these individually. So if I look at the mass indexes, the mass index here, the lowest value looks like it's about 33.1, and the highest value looks like it's about, I think about 54. So what I'm going to do here, I'm going to break the graph. I'm going to start here at 30 and count by 5s. There's 40, there's 50, and then I only have to go up to about 55. Here I'll do that to 60. Now, when I look at my residuals on my calculator here, it looks like my biggest residual is about 207 in the positive. In the negatives, it doesn't look like it goes more than negative 100. So what I'm going to do for my scale is I might count by 50s here and go like 50, 100, 200, and then do the same thing down. So that's negative 100, and I don't have to really go past that. So now I just need to graph these points. So the first point was 36.1, negative 73. So I'm just estimating it to the best of my ability. So 54.6, negative 87. Okay, get another point. 48.5, 29 or so. Okay. 42, 207, so that's that high point there. 50.6, 87, or sorry, 85, 42, 45, pretty low there. 40 and 19, so almost on the axis. 33 and negative 83, so down here. 42 and negative 95. 34 and 21. And the last one was 51 and negative 81, so something about right there. So 2, 4, 6, 8, 10, 11 points. Looks like I did pretty well. Let me just go back to the graph. Does my graph here look very similar to what I graph here? It looks like I missed one. So I must have missed one right here. So 1, 2, 3, 4, 5. So anyway, we got our residual graph here. So the hope and goal is that it doesn't seem like there's any pattern going on. That's our hope. If there's a pattern, then the line's not a good fit. If there is, or if there's not a pattern, the line is a good fit. So since this doesn't show a pattern, what I would say is something, since our residual plot does not show a distinct pattern, our least squared regression line fits our data well. And that's how we use residual plots to help us interpret it. All right, B says, which point has the largest residual? So we want to know basically which point is the farthest away from the x-axis. So if we look at that, that's this point right here. So if I go back to my stat, edit, that was that point that was sitting at like 207. So the question is, what does that actually mean in the context of the problem? I'm just moving this up a little bit so it's easier for me to write this. Okay? So we need to interpret this value or this residual value. So we would say something like this: a residual value of 207.74 means that our least squared regression equation underestimated the metabolic rate by 207.74 calories at the given mass of 42 grams. Or not grams, sorry, kilograms. Oh, that would be a difference in weight right there. All right, so remember what this does is this gives us that distance from the observed to the predicted. This is like saying the predicted. Whoops. This is your predicted y. Okay? This distance is kind of like saying where my observed y was. Well, my predicted y was way off. It was 207 calories off. So that was the one point that, I guess was the worst in the worst case scenario. While the rest of them, yeah, were pretty darn good. We're all within 100 calories, which is actually pretty darn good. All right. Next page. Number 3 asks us to still work with this problem, and it says, for the regression you performed earlier, so for this problem, r squared was 0.768 and s was 95.08. Explain what each of these values mean in the setting. So remember that r squared is the is the percent of variation, okay, in the y values that can be determined by the least squared line, and s is the prediction error. So how we would interpret that, so to start off with r squared, we would say 76.8% of the variation in the predicted, and now I put the y, what the y value represents was metabolic rates, can be determined, or you could use the word explained, by the least squared regression equation or line. So now, S represents the prediction error. Okay? So we would say our least squared regression equation has an average prediction error of 95.08, and we want to use the units calories when predicting the metabolic rates when knowing the person's body mass. All right, that takes care of your CFU for 3.5. We'll see you later.